Hello, in this video we're going to show that the max power of a turbine is 1/3 assuming perfect efficiency. So the max power of the ratio between the outlet and the inlet. So here we have our turbine here, and we have an inlet which we'll call position 1 and an outlet which we'll call position 2. So here in the middle of the turbine here, there is an area and there's also a velocity, and the fluid that's flowing through, or the gas or whatever is flowing through, has some kind of density. And then similar, if we look at each of the plates, there's going to be an area, a surface area of the plate. There's also going to be a velocity flowing through, and then the density will remain the same for the material or the fluid flowing all the way through. But the velocity at the inlet is going to be different from the velocity at the outlet, because as it flows through, the velocity is going to change, and then also the area is going to be different because the area at the inlet is going to be slightly bigger, and so we have the V1 and V, or the V1 and the A1 for the inlet, and then the V2 and the A2 for the outlet. So that's going to be velocity and area. And so what we're going to start with is the momentum balance equation. And so what this expression is it's that the change in the mass times the velocity of the system is with respect to time is equal to the mass flow in times the velocity in minus the mass flow out times the velocity out plus the force. And so looking at this specific problem, the mass flow is going to be equal in and out, and it's going to equal the density times the area times the velocity. And so if we plug this in for these equations here, we are going to have we can distribute out the mass flow since they were equal with one another. So we'll have the density times the area divided by times the velocity is equal to, in we have as the inlet is the velocity at 1 minus out is 2, so we'll have the velocity at 2 plus the force. And then because we're going to assume it's at steady state, the change in the mass times the velocity of the system is equal to 0, and so we'll set this equal to 0. So what we can actually do is move the force to the other side, so we'll have a negative force is equal to the density times the surface area times the velocity times the velocity of 1 minus the velocity of 2. And then what we can do is we can look at the power, and so it's important to note that between the plates, the force and the velocity have to be going the same direction. And so when we look at the power, it's going to be a negative force times the velocity. And then so if we plug this in for this velocity equation here, in for velocity, or this negative force equation, and for this negative force, we'll have the density times the area times the velocity, and then we have another velocity here, so it'll be velocity squared times the velocity at 1 minus the velocity at 2. And so that's the power if we're using the momentum balance equation. And so we can also use the kinetic energy balance equation. And so what this is that power is equal to the change in kinetic energy over the mass flow. It's the change in kinetic energy over the mass times the mass flow. So what this is going to equal is going to equal the velocity at position 1 squared minus the velocity at position 2 squared divided by 2 times, again, we talked that the mass flow is the density times the area times the velocity. And so now what we can do is we can actually set these two power equations equal to one another. So we'll have the velocity at 1 minus the velocity at 2 times the density times the area times the velocity squared is equal to the velocity at 1 squared minus the velocity at 2 squared divided by 2 times the density times the area times the velocity. And so now what we can do is we can cancel out the densities, we can cancel out the areas, and we can cancel out this velocity on the right, and that leaves, because this one is squared, we'll just get rid of the square on the left. And so now what we can do is we can actually isolate this velocity here. And so if we isolate the velocity, we can distribute out this velocity 1 squared minus velocity 2 squared. So that's going to be velocity 1 minus velocity 2 times velocity 1 plus velocity 2 divided by 2 times velocity 1 minus velocity 2. And so these two quantities will actually cancel out, leaving us with velocity 1 plus velocity 2 divided by 2. And so now what we can do is we can actually plug this velocity back into one of the power equations. And so we can just use this power equation here, the kinetic energy balance equation. And so if we were to plug this in, we would have velocity at 1 squared minus velocity at 2 squared divided by 2 is equal to the density times the area times velocity 1 plus velocity 2 divided by 2. And so now what we can do, these should not be equal to one another. These are just multiplied with one another. So this is the power equation, it's equal. And so this is power is equal to this. And so now what we can do is we can clean it up a little bit. So we'll have the density times the area, and then the 2 in the denominators will multiply to give us 4. And so now we can do the velocity 1 minus squared minus velocity 2 squared times the quantity velocity 1 plus velocity 2. So what that will give us is, if we distribute it out, we'll have velocity 1 times velocity 1 will give us velocity 1 cubed, so velocity 1 squared times velocity 1. And then we have velocity 1 squared times velocity 2, so we'll have v1 squared v2, and then we have the negative times a positive, so we'll have minus velocity 2 squared times velocity 1, and then we'll have velocity 2 squared times velocity 2, again a negative times a positive, so that would leave us with a negative, so we'll have velocity 2 cubed. And so now what we can do is we can divide across by velocity 1 cubed. And so that will give us the power is equal to distribute out velocity 1 cubed. And so we'll have the density times the area divided by 4 times velocity 1 cubed distributed out, so divided by velocity 1 cubed is going to leave us with just 1. Then we'll have plus. We have the velocity 2, which will remain the same. If we divide by velocity 1 cubed, that will give us a velocity 1 in the denominator, minus the velocity 2 squared will remain the same, divided by, we'll have velocity 1 cubed in the denominator, so cancels out with that one. That will leave us with velocity 1 squared in the denominator. And then minus again, we'll have the velocity 2 cubed will remain the same, and then we're just dividing by velocity 1 cubed. And so if we were to define R as the ratio of the velocity out, so that would be velocity out divided by velocity in, so that would just be v2 divided by v1. What we can do is we see this is just going to be r. This is going to be r squared. This will be r cubed. And so if we take the derivative of the power with respect to r, that will give us 1 minus 2r minus 3r squared. And I made a mistake here. I said that we would distribute out the velocity 1 cubed. I forgot to write it up here. So velocity 1 cubed. And so now what we can do is we look at this 1 minus 2r minus 3r squared, and we were to set it equal to 0 and we factor it out, that would give us 1 minus r times 3 minus r, and so is equal to 0. I factored it wrong. It's going to be 1 minus 3r, and then 1 plus r is equal to 0. So that's going to give us r is equal to 1/3. So then the velocity out with ratio to the velocity in is equal to 1/3. So that's the ratio of the outlet to the inlet for the maximum power assuming perfect efficiency.